Hi guys, in the previous lecture we have solved some previous year gate problem based on network theorems. Okay, and in this lecture we will study about the steady state response and we will solve some previous year gate problem based on a steady state response. Okay, let's talk about the steady state response. Suppose in any LTI system is linear time invariant system. If xt signal is passing through any LTI system, then the response of the system contains two components. One is the transient component and second is the steady state component. Okay, the transient component decay as the time passes if this system is stable. Okay, I am considering that the LTI system is stable, means the transient response of the system decays as the time passes, and at a steady state I will get only a steady state response. Okay, we will study in detail about the transient response in the coming lecture. Okay, right now we will study about the steady state response. Let us take this circuit. The circuit is the combination of resistance and capacitance, and we have to find the voltage across the capacitance. That means we have to find the response across the capacitor. So in this circuit there are two methods to solve this circuit. First is the time domain approach, and second is the frequency domain approach. If I will solve this circuit by using time domain approach, then I will get first order differential equation, and I will have to solve that first order differential equation in order to find the response of the system. Okay, suppose in this circuit, if I will connect one inductor and if I will solve this circuit by time domain approach, then I will get second order differential equation, which is little bit complex to solve, because when I will solve the second order differential equation, then I will get two constant, and we have to find the two constant by taking the initial condition, then finally you will get the output of the system. So in order to reduce the complexity while finding the response of the system, we use frequency domain approach. Instead of using time domain approach, we will use frequency domain approach. Okay, by converting this circuit into frequency domain, and after that we will find the transfer function of that system, which is given by Laplace transform of output upon the Laplace transform of input. Okay, and we will convert this whole complex network with one block given as h of s. H of s is the transfer function of LTI system. Okay, which is given by Laplace transform of output upon Laplace transform of input. So we represent this circuit in frequency domain by one block whose transfer function is given by h of s. Okay, now we will give input ai sine omega naught t plus phi I, where ai is the maximum input signal and omega naught is the input frequency, whereas phi I is the input phase. Okay, so if I will give signal to this LTI system, then the output of the system is given by ai a naught sine omega naught t plus phi I plus phi naught. Okay, means the frequency of the output signal will remain same as the input, because this system is LTI system. Okay, however the magnitude and the phase angle may differ. Okay, so in order to find the a naught and phi naught, a naught is given by magnitude of this transfer function h of j omega at omega is equal to omega naught, that is the input frequency. Okay, while phi naught is given by angle of h of j omega at omega is equal to omega naught, that is input frequency. So this is the steps applied to find the steady state response of any system. Got it? What I will do, first I will convert the whole electrical network in terms of transfer function in frequency domain. Then I will represent that in terms of block that is given by h of s. Now I will apply the input signal, and the output signal is given by ai a naught sine omega naught t plus phi I plus phi naught. Means there will be change in magnitude and the phase, however the frequency of the signal remains constant. Means it will be equal to input of the frequency of input signal, because this is the LTI system. Got it? Let us solve some problem, then you will come to know how to find the steady state response in any circuit. Okay, let us take this example. In this example, we are giving input signal 2 sin t, and we have to find the steady state output voltage V0. See, I already told you the steady state output V0, since this is LTI system, means the steady state output V0 is given by 2 A0 sin t plus phi naught. Okay, according to this, if I am giving input Vit is equal to ai sin omega naught t plus phi I, then the output of the system is given by ai a naught sin omega naught t plus phi I plus phi naught. Okay, so in this system phi I is 0, omega naught is equal to 1, hence output of the system is given by 2, that is ai a naught sin omega naught t plus phi I is 0 plus phi naught. Okay, now we have to find the a naught and phi naught in order to find the steady state output voltage V0. I already told you how to find A naught, since h of s is given by s upon s plus 1. So in order to find the A naught and phi naught, we have to first find the h of j omega and mode of h of j omega and angle of h of j omega. Okay, let's find h of j omega. H of j omega, put s is equal to j omega, you will get j omega upon 1 plus j omega. Now mode of j omega is given by omega upon under root 1 plus omega square. Similarly, angle of h of j omega is given by 90 minus tan inverse omega. See, numerator having angle j means 90, and the denominator having angle tan inverse omega. So when it will go to numerator, then overall the angle become 90 minus tan inverse omega. Okay, now we know that at omega is equal to 1, since the input signal have omega is equal to 1, that means a naught is equal to magnitude of h of j omega at omega is equal to 1. Means if I will put omega is equal to 1 here, then I will get 1 by root 2. Okay, 1 upon under root 1 plus 1, that is equal to 1 by root 2. Similarly, to find the phi naught is equal to angle of h of j omega at omega is equal to input frequency, that is 1. So I will get 90 minus tan inverse 1. Tan inverse 1 is equal to 45. So overall 45 degree. Okay. Hence the steady state output voltage V0 is given by 2 multiplied by 1 by root 2. A naught is 1 by root 2 sine t, and the phi naught is 45 degree, means plus 5 45. So this is the steady state output response of the system. In this way we can calculate a steady state response of any LTI system. Got it? Let's solve some gate problem. See, this is the RC circuit given, and we have to find the steady state output voltage V0. Okay, so what I told you, you can go with the time domain approach also, and you can go with the frequency domain approach. So I will prefer frequency domain because it is easy to solve. So first I will find the transfer function of this circuit. First step number 1 is to find the transfer function of this circuit. Transfer function is nothing but V naught of S upon Vi of S. Okay. So let us convert this circuit into S domain. You will get R this is 1 upon Cs. The capacitance, the capacitive reactance is given by Xc is equal to 1 upon J omega C. So put J omega is equal to S, you will get 1 upon Cs. This is V naught upon S, this is Vi upon S. Okay. Now apply voltage division rule. V naught upon S is given by total Vi upon S multiplied by the reactance, that is the impedance of here, that is 1 upon Cs by total impedance R plus 1 upon Cs. So you will get V naught S upon Vi of S, that is equal to transfer function is equal to 1 upon 1 plus RCS. Now this whole circuit can be replaced by with one block having transfer function is equal to 1 plus 1 upon 1 plus RCS, and this is my output, that is the response of the system, and this is my input. Got it? Now see, we have given the input signal which is the combination of DC plus AC. Okay, means the output you will get V naught is equal to 3 multiplied by this. First I will take the DC signal, 3 multiplied by some magnitude, let us take A1, and this will not have any frequency because this is constant. Okay, plus now take AC component. AC component have 4 into A2 sine 100t plus phi naught. Okay, where A1 and A2 can be found by taking magnitude of this transfer function. Similarly, phi naught can be found by taking angle of this transfer function. Got it? Now first find the magnitude of this transfer function. Let us take it as a h of s, means magnitude of, we have to find magnitude of h of j omega, that is equal to 1 upon 1 plus RC j omega, that is given by 1 upon under root 1 plus R square C square omega square. Okay, similarly angle of h of j omega is given by minus tan inverse RC omega upon 1. So first find the magnitude of transfer function and angle of transfer function by supplying DC signal, that is 3 volt. Since DC signal has 0 frequency, means it does not have any frequency, means omega is equal to 0. So at omega is equal to 0, I will get magnitude of h of j omega is equal to, put omega is equal to 0, you will get 1. Okay, and angle of h of j omega is equal to minus tan inverse 0, means 0 degree. Okay, this is for DC. Now find the transfer magnitude of transfer function and angle of transfer function for AC signal. So AC signal has omega is equal to 100, means at omega is equal to 100 I will get magnitude of h of j omega is equal to 1 by under root 1 plus 100 square into 1k square, that is r square, into 10 to the power minus 5 square. You will get h of j omega is equal to 1 by root 2. Similarly, find angle of h of j omega. Angle of h of j omega you will get minus tan inverse rc omega upon 1, that is equal to minus tan inverse rc is given by 10 to the power minus 5 multiplied by 10 to the power 3, that is equal to 10 to the power minus 2 multiplied by omega is equal to 100 upon 1, which you will get minus 45 degree. So minus 45 degree. Now multiply, this is my a1, okay, this is my a2, and phi naught, this is my phi naught. So finally you will get v naught is equal to 3 multiplied by this. Why I am considering a1 as this? Because for DC at omega is equal to 0 I am getting h of j omega, magnitude of h of j omega is equal to 1. So this is my DC signal. So we have to multiply the corresponding magnitude with the DC signal. Similarly, we have to multiply the corresponding magnitude for AC signal. Got it? So 3 multiplied by 1 plus 4 by root 2 sine 100t minus 45. This is the answer. Let's take one more problem. An input voltage Vt is equal to 10 root 2 cos t plus 10 root 5 cos 2t plus 10 is applied to series combination of RL. Determine the resultant steady state current. First draw the circuit. This is my input voltage Dt having series combination of RL, and we have to find the steady state response, that is the current. This is R, this is R. So what I told you, first convert this circuit into transfer function of the system. Okay, now see, transfer function is given by output upon input, Laplace transform of output. What is the output we have to find? We have to find the steady state current, means output is Is and input is given by Vs. This is my transfer function, that is h of s, and this is also be represented by 1 upon Zs. Is upon Vs is equal to 1 upon Zs, that is equal to admittance y of s. Okay, so the impedance of the system is Zs is equal to R plus L. In S domain, the inductive reactance is given by Ls, that means R plus Ls. Put the value of R is 1, L is 1, 1 plus S, means H of S is equal to 1 by 1 plus S. Now replace the whole circuit with one block having transfer function 1 by 1 plus S, and input is given by Vt, and we are taking output It. So Vt is given by 10 root 2 cos t plus 10 plus 10 root 5 cos 2t plus 10, and this is LTI system. Then the response of the system It is given by change in magnitude, that is 10 root 2 A1 cos, frequency remains same, t plus 10 plus phi 1, okay, plus 10 root 5 a2 cos 2t plus tan plus phi 2. So find first magnitude of transfer function. H of s is equal to 1 by 1 plus s. H of j omega is equal to 1 by 1 plus j omega. Hence magnitude of h of j omega is equal to 1 by under root of 1 plus omega square, and angle of h of j omega is equal to minus tan inverse omega. Okay, now find a1 and phi 1. a1 and phi 1 can be found by putting omega is equal to 1. So if we will put omega is equal to 1 here, then magnitude of h of j omega at omega is equal to 1 will be 1 by root 2, and angle of h of j omega will be minus tan inverse 1, that is equal to 45 degree. In order to find a2 and phi 2, what I will do? I will put omega is equal to 2 in transfer function. So putting omega is equal to 2 in this mode of transfer function, I will get a2 is equal to 1 by root 5 and phi 2 is equal to minus tan inverse 2, that is equal to minus 63.43. Put the value of a1 and phi 1 in this equation and a2 and phi 2 in this equation, you will get response of the system. Got it? Now let's take this problem. We have to find the steady state current in this circuit. Okay, a steady state current. First I will find the transfer function of this system. The transfer function is given by Laplace transform of output, that is equal to it means is, and Laplace transform of input is given by 5 plus 10 sin t, that is voltage Vs, that is equal to y of s is equal to 1 upon z of s. Now find z of s of this circuit. Z of s is given by R plus inductance Ls plus capacitance 1 upon Cs. Put the value of RLC. 1 plus 2s plus 1 upon s. You will get 2s square plus s plus 1 by s. Hence y of s is equal to transfer function is equal to s upon 2s square plus s plus 1. Now we can replace this whole circuit with one block having transfer function this, and now we will supply Vt as an input. Okay, now we replace the whole circuit by one block having transfer function s upon 2s square plus s plus 1, and we have given the supply Vt is equal to 5 plus 10 sin t, means the steady state response it is equal to what? 5 into a1, that is the magnitude, and since this is the DC, so it does not have any phase displacement, plus 10 into a2 sin t plus phi 2. Okay, we will find a2, phi 2, a1 by using this transfer function. So first find h of j omega. H of j omega is equal to j omega upon minus 2 omega square plus j omega plus 1. Okay, first find at omega is equal to 0. Since DC have omega is equal to 0, so I will find first omega is equal to 0. What is the h of j omega? H of 0 is equal to 0 upon 1, 0 upon 1, 0 plus 0 plus 1, that is equal to 0. And since this is DC signal, so there will be no any phase displacement, so this is equal to a1. Now find the response with sinusoidal input. Okay, so at omega is equal to 1, since this sine wave has a frequency is equal to 1, so h of j1 is equal to what? J upon minus 2 plus j plus 1, that is equal to j upon minus 1 plus j. So if you will calculate magnitude of h of j1, you will get 1 by root 2. Okay, and the angle of h of j omega is at omega is equal to 1 is given by minus 90. And see, this is in second quadrant. See this is minus 1 plus j, so this is in second quadrant. Okay, so this will be measured from minus 180 minus tan inverse 1, which you will get 90 minus 135, that is equal to minus 45. This is my phi 2, this is my a2. So put the value of a1, a2 and phi 2 in this equation, you will get the response. Okay, that's all about this lecture. In the next tutorial we will see transient. So before going into transient, I would like to tell you, you should read the concept of charging and discharging of inductor in series with resistance. Okay, means charging and discharging of RL and RC circuit. Okay, what are the equations of inductor current and capacitor voltage while charging and discharging. Okay, you should read this concept. If you guys are having any doubt, then you can join our Facebook group and ask the query. For new updates, you can subscribe to this channel. Thanks for watching this video.